Hey, good morning, team. So today is Wednesday, the 11th, maybe the 11th, I think. I am so sorry I cannot be in. There's all sorts of craziness going on. I should be in tomorrow, and I know that's delayed our project. So for today, I want to take some notes on something that honestly it works out well. It kind of takes up the whole day otherwise. And it's an easy enough concept. So we are taking notes on power. We've talked about work, we've talked about energy. Now we are talking about power. So the way I normally discuss this is to get two textbooks and I put them in both hands and I lift one up and then I lift the other one up to the same height, but I do it really, really quickly. So I lift one slow, one height. And I ask everyone if I did more work in one than the other. And the temptation is to say I obviously did more work in the one I lifted quicker, but that's not true because I lifted them to the same height. If I lifted them to the same height, I did the same amount of work. The only difference is I did the same amount of work quicker with the one of them. And that is exactly what power is. Power is the rate at which a system does work. If you have more power, you can do more work over the same amount of time, right? So I did the same amount of work. It's just the textbook I lifted really quickly. I did it in less time. Therefore, because it was less time, I had more power. So that's the equation for power. Power is work over T. And the long and the short of it is the more power you have, the quicker you can do work. That's power. Honestly, that's it. And we're done. We're not done. We're not done. That's a lie. But I'll pause it and then go on to the next slide. Or you can pause it, take notes, and then we'll move on. All right, so power is the rate at which a system does work. It's the work divided by time. It has a different unit. So arguably, the most sensible unit would be joules per second. However, we don't really say that. What we actually end up saying is 1 watt. So if you have 1 watt of power, you can do 1 joule of work every second. It's named after this dude, James Watt, who was a mining engineer. And if you actually break down the units, you end up with this, joules is kilogram meters squared per second squared. You're dividing it by another second. You end up with this horrible unit, kilogram meter squared per second cubed. So yeah, watts is definitely better. But you want to think of watts as joules per second. That's the easiest way of thinking about it. Oh, excuse me, it is a scalar. It doesn't act in any one direction. I got a cough more. That was a jolly good cough there. And the only other unit you may have heard of is horsepower. No one really uses that in reality. It's just advertisers use it for cars and engines and that because it sounds sexy, doesn't it? Horsepower versus watts. It sounds better. But the funny thing is, um, a horsepower isn't really the power of one horse. So horsepower was designed. It's kind of a similar thing. The work would be lifting 550 pounds 1 foot. Obviously, this was a long time ago, so they didn't use decent units in 1 second, and that's what they considered 1 horsepower. But the average horse back then was very small. The horses he was talking about was very small because they were the kind of miniature horses that you would fit in mines, like coal mines and that. So they had to be small to fit in the tunnels. And yeah, generally speaking, the average horse has like anything between 7 and 15 horsepower nowadays. So it's kind of silly, isn't it? But there you go. So let's just do a couple of worked examples to make sense of this, and we are done. All right, so worked example number one. We have got a crane. I would draw a picture. I don't have my pen with me, unfortunately, so I've got to kind of do it all printed. But I have a crane. This crane can lift 100 kilogram mass 8 meters in the air, and it takes 5 seconds to do that. What is the average power delivery of the crane during this time? This is not a tricky question. In fact, it is a beautiful plug and chug question because so cranes lifting 100 kilograms is the mass it's lifting at 8 meters in the air, does it in 5 seconds. So let's just start with our equation. Power is equal to work divided by time. Well, work, when you're lifting, work is just force times distance, right? So let me plug that in. Power is equal to force times distance divided by time. And then when I'm lifting something, the force of gravity pulling down on it is mg. So the amount of force I have to push up on it also has to be mg. So power is equal to mg is the force times the distance, which I guess in this case is the height, divided by time. And I think that's everything, right? Because I know what the mass is. It's what is it? 100 kilograms. G is 10. The height I lifted it is 8 meters. I do that in 5 seconds. So I plug all those numbers in, and I have a unit of 1,600 watts, or 1,600 joules per second. That's not too bad, is it? Except this, hang on, For some reason I had the height as meters per second, but it's meters. And then you look at it, kilogram, meter, so meter squared, per second, so that's per second cubed. There's your watts. Done. Okay, so there is another type of, I mean, it's about as simple as it gets. It really is one of the easiest concepts. But there is a slightly more complicated version of this. It's really not that complicated at all. And it's a constant velocity problem. If you have, how much power do you need in order to be moving a constant velocity? So how much power does a car need to push through 70 miles an hour? Now, in order to do that, you need to know the force pushing against the car. So I'm using this one as an example. How much power is needed to push a 250 kilogram skidoo, ski machine? What do they call them? Skidoo. I just call them skidoo. Through the snow at a velocity of 80 meters a second, when the coefficient of friction is 0.3 between the snow and the skis. All right, intimidating. Yes, definitely draw a diagram. I don't have my pen. I can't draw a diagram. So I'm just going to work through this with the equations. I know power is equal to work divided by time. That's my new equation I just found out. I love it. It's a great one. I know that work is equal to force times distance divided by time. Okay, that's good. I know that. I know that the only force, for argument's sake, acting against the skidoo is friction, and I know friction is equal to mu times the normal force. So let's plug that in. Power is equal to friction, so mu times the normal force, which is mass times gravity. We're on a level, if I'm going up a hill, then we've got problems, right? But I'm not. I'm assuming I'm on a level surface. So the normal force is, you've got gravity acting down, you've got this equal and opposite force acting out, mg. So now I have power is equal to mu times mass times gravity times distance divided by time. But here's the funny thing. I need velocity. Well, I'm going a certain distance divided by time. Distance divided by time, right there, that is my velocity. So power is equal to mu times mass times gravity times velocity. Again, the velocity is equal to distance divided by time. So I'm just going to abbreviate that to velocity. And I'm done. All I've got to do now is plug in my numbers. So mu is 0.3, mass is 250, gravity is 10, my velocity is 18, and that is it. I am done. You multiply all that together, it's telling me I need 13,500 watts skidoo in order to move at a constant velocity. Yeah, that's not too bad, is it? Alright, so I don't think I want to waste a day doing this, but this is the actual lab that we normally do for power, where basically we need to do work and we time it, and then we figure out what our power is. So the easiest way to do work is to change our gravitational energy. So what I do is I get someone, I get all of you actually, I make you run up the stairs, you time it. Well, you can figure out how much work you did because, again, it's the change in potential energy or even just the force times distance is mass times gravity times height. That is your change in potential energy, so that's your work. And then you divide it by the time, and you figure out what your power is. And it's normally around a horsepower, actually, funnily enough. So that's kind of interesting. I'm not going to do that, but I just want you to know that. But what I do want to do is I want to give you an exit slip, which is this guy. 200 kilogram boat accelerates from rest to 18 meters per second in 6 seconds. I should put an S there. Calculate the power delivery of the engines during this time. Alright, so this is not a constant velocity situation because I'm going from rest and I am accelerating to 18 meters per second. So you can't actually use the method I just told you, but what I do want you to remember is that power is work divided by time, but work is also the change in energy or the change in kinetic energy. When we start, the boat has, go back. When we start, the boat has 0 kinetic energy because it's at rest, and then after the 6 seconds, it has a certain amount of kinetic energy, which you can easily calculate because it is moving, and the change in kinetic energy is the work. So use that work in the calculation and you'll be fine. Put that on the little survey thing I'm going to put on the Google Classroom. Done for the day. Hopefully I'll be in tomorrow, so I am out again today. But I hope you get this right. Any questions, email me. All right, take care. Bye. Bye now.